All right. Hello, everyone. You are here. Okay. All right. So can I have your attention, please, back to the class? Okay, good. So let's continue on what we started. If you recall, on Wednesday, we said we stopped vibration, and just do a quick review to refresh your memory from what you've learned in dynamics before. So, and also in Mech 360, we started with modeling, right? How we can model, let's say, a cantilever beam, or let's say a bar to a spring, because that's something that we need in this course. We like to deal with the springs, right? And you saw how we can, like, for example, a cantilever beam, change it just to a linear spring, or similarly, a simple beam, how you can change it to a spring. And similarly for a cable, and then later for something which is under torsion, right? After that, we said we are going to spend like short or a brief, we are going to do a brief review of dynamics. So for those of you who have forgotten the dynamics, if you have a particle, we have the Newton law, which is simply sum of the forces is equal to ma. This is all we need in this course. And if it is a rigid body, it means it has dimension. Then we have mass, and we have something else which we call it mass moment of inertia. We show it by I, and we use Euler formula. Euler formula is the first law is very similar to Newton. It says that sum of all the forces is equal to ma, but this time because we are dealing with a part which has dimension, this a is a bar, or when we show an a bar, we mean like the acceleration around the center of gravity. Sometimes we show it by g, like in this picture. All right, so that's a sign that we use. And the second law of Euler says that since now it has dimension, it can rotate. Sum of all the moment about this center of gravity is equal to I bar alpha. What is alpha? Is angular acceleration, right? And we have like a special case, which it happens a lot. We, rather than like having a, let's say a part that's floating on a plane, let's say a part is fixed to the ground. So it has an alpha and it has an omega. Omega this time is not the natural frequency, it's the angular velocity. And this time we can write sum of all the moment about point O, the point that it has been fixed and it can rotate, is equal to IO alpha. All right? So that's what we reviewed last day. And then we said, again, most of you know this, but a quick review about moment of inertia. So mathematically, moment of inertia, if again, you recall, if we say we have, let's say, a particle with mass m, just a small particle, no size. So it has one property, which we call it mass. We are familiar with mass. Another property is moment of inertia, which I can take the moment of inertia, let's say about any point, IO, and it defines IO mathematically as m r squared, which r is the distance between that particle and point O. Right? So this is the definition of mass moment of inertia, and in a general form, I is defined as r for the distance dm, sorry, r squared dm. Sometimes people call it second moment of inertia because of this r squared. But moment of inertia or mass moment of inertia is the terminology that we will use. Okay. So that's the definition, but we don't need that definition. We just use mass moment of inertia for some members which we encounter a lot in this course. For example, we encounter a lot a slender bar. We may encounter like a box, more like a box, and a disc, like these three shapes that I showed. So it's stick in your mind, but these are the three most common shapes that we use. About the first one, let's say the disc and a slender bar, we can say they are in fact cylinders, right? But cylinders that the first one, let's say the disc has a very short height and the slender bar has a very small radius. For a cylinder, if we look up the tables, then we can find out that the mass moment of inertia about the three axes, let's call, doesn't matter what we name them, but let's call this one Z, like the normal one. And then if that's the Z, then it has to be X. And this one has to, sorry, this one, let's call it X. It's more intuitive to call the horizontal one X and the vertical one Y. But it doesn't matter how to name them, right? So it's a cylinder. And let's say this cylinder has a radius R. And it has a length L. So for this cylinder, if you look up the table, the IX and IY, because of symmetric, they are equal. And they are equal to 1/4 m R squared plus 1/12 m L squared. That's Ix, and Iz is equal to half of m R squared. This is like all the formula that we need for mass moment of inertia for a cylinder. Let me create some room here. And okay, so now when we get to let's say a slender bar, and similar concept, let's say I have the z-axis, the x and y-axis. So x, y, and z-axis, right? So since it's a slender bar, we assume R is very small and compared with the rest of the size. So we can approximate and say that Iz is almost 0, and that's good enough, it's acceptable. And Ix and Iy is equal to 1/12 m L squared. So replace it with that cylinder, except R is small, so you ignore it. And when we get to the disk, let's say the disk again, if I call like this axis to be X, Y, and then Z is the normal at the center of these disk. So let's assume that it has a radius R, and the thickness of this one, let's say, is something that we can ignore. Or in some problem, if it gives you the thickness, then you have to treat it as more like a cylinder. But if it didn't mention, like if the question doesn't mention the thickness of that cylinder, it means that you can simply ignore it. So for this one, Ix, I write it down here, Ix and Iy, they are equal. And they are equal to 1/4 m R squared. And Iz is half of m R squared. Okay, so then simply if we saw like a disk, and the question didn't, like the question, let's say, doesn't mention the thickness of that things, it means you can ignore the thickness and write down the Ix, Iy as that. If it is a cylinder and you want to be more accurate, then you can use the whole formula as it is. And if it is like a slender bar, and then the question doesn't mention anything about the radius of this bar, just talk about its length and its mass, then simply use this formula. And a box, which more like this box, let's say has dimension A, B, and H. Then about 3 axes. And again, remember these axes are passing through the center of gravity. Maybe you should do a better job here and show them like that. Okay, so this is the center of gravity. And we can call, let's say, this one to be X, and this one Y, and this one Z. Again, the naming doesn't matter. So for a box, it's easy to remember. For each side, for that axis, normal to that axis, like Iy, for example, is 1/12 m, and the square of that, the square that we see on that side, which is A and B, is A squared plus B squared. Right? So like axis Y is normal to this side, which has the dimension A and B. It's simply Iy is 1/12 m A squared plus B squared. And if you need AZ, then simply it is 1/12 m A squared plus H squared. And similarly for Ix. And you should remember this formula because you will use them frequently in this course later, and they come a lot in calculation. So we better remember them. If not, they are all, if you just Google moment of inertia for a cylinder or for a slender bar or for a disk, you will see the formula. Okay, and all these things came from the main definition that we define I moment of inertia as integral of r squared dm. So for all of these, we can integral all and we get that form. Okay, so that about mass moment of inertia. One more thing about mass moment of inertia is sometimes we need to transfer the axis. It means, let's say I have the moment of inertia for a bar, but I need it for a different place or different point. So there is like this simple formula which tell me if I have a mass m, and let's say this mass m, it has a center of gravity g, and I have I. So in order not to get confused, usually the moment of inertia that passed through the center of gravity, you show it by I bar, or you can just write IG. And let's say for some reason I need I for a different point. Let's say this is the point that I need, and that point doesn't have to be on the mass itself, right? So new axis. So I would say I nu is equal to I bar plus mass multiplied by the distance between these two parallel axes squared. And this is called the law of parallel access theorem, or the parallel access theorem, or whatever you want to call it. So you just need to remember, you can only transfer mass moment of inertia if this side of the equation, it is I bar. Okay, if you have I bar, then you can write this equation. So always this side of the equation, on the right side, you need to have I bar, nothing else. So with that, if I have, let's say, a slender bar, so as an example, let's say I have a slender bar, mass m, and length L. And I like to know so I have I bar, which is for the center, and it is 1/12 mL squared. Now I need I/O. Let's call this point G, center of gravity. And remember, mass moment of inertia is not about a point. For simplicity, we say about this point or about that point. Always it's about an axis, right? Remember what we had here? I draw axis X, Y, and Z. Right? Now, like for this slender bar, the axis that I'm referring is coming out of the screen. It's normal to the screen coming out of the screen, but for simplicity, we just talk about it as a point. We say IG or IO. But in fact, we are talking about an axis coming out of the screen. This is about axis passing, or let's say at point G, normal to the screen. So what is IO? So simply IO is I bar plus mass and the distance between these two axes, right? These two parallel axes, they come out of the screen, which is L/2, and it gives me 1/3 mL squared. And another terminology that we use a lot in this course, and the experimental test that you will do, in fact, you measure these things, it's called radius of gyration. It's more like a mathematical term. Usually working with I is a big, because it's a big number, it's not convenient. The unit of I, let's say if I write I for like a simple mass, it was, if you remember, R squared M, right? Or MR squared. For like a simple mass, M at point O, IO is, and the distance here, call it R. Like for this simple mass also, you can use this transfer axis because the particle doesn't have any mass moment of inertia. So IO, you can find it is MR squared. So obviously the unit, you can say the unit for mass moment of inertia is kilogram, for example, meter squared, or pound inch squared, right? And usually it's a big number and inconvenient to work with. one way to solve that one is to define something which we call it radius of gyration. We show it by R. In some textbook, they show it by K. But since in this course we use K, we reserve K for a stiffness. We don't want to get confused. We show it by R. But if you see on other textbook, K is like they use. And it defines that I square of I divided by M. So we divide mass moment of inertia by its mass and we square it. So now it has a unit meter. Or inch or whatever length that we use. It's a smaller number, it's more convenient to work with. Okay, because R now is a distance. Right? So conceptually, if you want to get a feeling what is radius of gyration, think about it as like this. Let's say I have a mass M and it has a center of gravity G, all right? And let's say it has a moment of inertia I about G. Coming out of a screen, okay? So I would say, what is the equivalent ring, like a ring if I can draw a ring, maybe let me use my circle things. I should have somewhere. Like conceptually, we can say, let's say you have a mass, whatever shape it has. It might be a slender bar, it might be a box, it might be a disc or whatever. I would say, what is the equivalent mass of, not equivalent mass, equivalent shape, if it is in a form of a ring that has the mass M and radius R, and these two have the same mass moment of inertia. So now this R is the radius of gyration. So question for you, what is the moment of inertia for a ring? It's also another shape that you should know the mass moment of inertia. Somebody remembers? Exactly. That's M R squared. So mass moment of inertia for a ring is mr squared. Okay. Now I say, what should be the R, the radius of this ring? So these two have the same mass moment of inertia. And this is where we get this R. So that's conceptually what we refer to radius of gyration. And mathematically, as you see it in over here. Is that based on the circle or is that going to the middle? Good question. That's it. That goes to the middle. When we refer to a slender ring, always the radius that we are referring, it is like the average radius. Like if I zoom over here, it is more like in the middle, the average. Okay, so I assume that you should be comfortable with this. It was just a review, and that's why I passed through this topic fast. But anyone has a question before we move forward? Okay, are we good? And again, you will see we will use them like these things a lot in examples. So you will become comfortable with this. So, and lastly, in terms of review is, you saw that we have two methods to solve problems, right? One was the Newton law or Euler law, and the second was the Lagrange equation or the energy method. For Lagrange equation, you saw that we need to find T, kinetic energy, and U, potential energy. So kinetic energy, again, for a particle, you are familiar. A particle has a velocity v, and so simply you say, if I have a particle m and it has velocity v, then the energy or the kinetic energy, which we show it usually by T, is half of mv squared. That's easy. You have used it a lot and you know what it is. Okay. So when it comes to a rigid body, we can categorize them to three categories. A rigid body that just translates, like the picture on the left, it just moves with the velocity without any rotation. The second one, it's being fixed to a point and rotate about the point, right? And the third one is a hybrid one, a combination of both moving and rotating, something like float. Okay, so let's say if you want to see it in one example, consider like a slider, like a crankshaft mechanism or a slider mechanism. So a slider mechanism, which again you are all familiar with and you know how it works, more like a cylinder and piston, right? Go left and right, back and forth. So for a slider cylinder, this is a member, right? This is one is member 1, 2, and 3, and 4. So this member 2, it has pure rotation. This member 4, it has pure translation, right? But member 3 has both of them. Like it has rotation plus translation. When we say rotation, it means like if I draw a line on it, after the mechanism moves, the angle is going to change. That line is going to change, so it rotates. Okay. So for each of them, we have a formula to calculate the energy. The first one is very simple. T is half of m v squared. More like a particle, no difference. Okay, so when we don't have any rotation, it's more like a particle, half of m v squared. When we have pure rotation, it's also is very easy. T is half of I O omega squared. Remember, moment of inertia about the point that it rotates, not I bar, I O. So this one then is also easy. And the last one you can guess is combination of these two. So we'll write T is half of m v bar squared. So it must be the velocity of its center of gravity, because now for this mass, since it has also rotation, the velocity at different points are going to be different. Plus half of I bar omega squared. So we need to be careful. This is V bar and this is I bar. So this is kinetic energy for 3 simple case. And if we have V bar and if we have omega, simply we can calculate it for each of these shapes. Now, let's just, for a quick practice, here's calculate it for one example. Let's say I have a disk. And this disk has a radius of R, mass M. So it has radius R, it has mass M, and let's assume that this thing is rotating with the velocity omega, and question told us that it rotates without a slippage. It is pure rotation without a slippage. And we want to find out T, its kinetic energy. Maybe you spend a minute, think about it, and then when I write, you can compare your result. Okay, so let me write it and then you can compare. So between these 3 categories that we have, it belongs to which one? Combination, exactly, because these things is nothing fixed to one point, right? And it's not a pure translation, because if I draw one line on it, like one horizontal line on it, then the next moment this line is going to have a different angle. So it means it rotates. It might be a small, but we don't care. But of course, it's not small. It's keep rotating. T, then it is half of, we follow that formula, half of M V bar square plus half of I bar omega square. We have omega, we have I bar, we need V bar. Since this is a disk, we assume it's uniform, then its center is at O, like center of this disk. So V bar, because the question gives us this extra information that there is no slippage. And again, from dynamics, you learn in that scenario, V bar is R omega. So if I replace V bar with that, I will see M R square omega square plus half of I bar omega squared. Right? And if I simplify this one, I will have half of mr squared plus I bar omega squared. But from the like the theory law of parallel access, we know I bar plus mr squared. If I call this point C, it is IC. So then for a disk, I can make this conclusion that if a disk rotates without any slippage, then simply T will be half of IC omega squared. Right, so, and this is true only if the disk does not slip, right? It's pure rotation without any slippage. And in fact, we can look at this way. We can think of it that this disk, because it rotates without any slippage, for a moment, I can think that it's being pinned to the ground at point C. So I can treat it more like the scenario number 2, right? This scenario number 2 was when the part has been fixed to the ground and rotates about that point. So for this disk, I can think of it as more like, for a moment, it has been pinned to the ground, and it is more like pure rotation about that point. That's why we can write it half of IC omega squared. And we know what is I bar and IC for a disk. We have the formula. So I bar for a disk is half of mr squared. And so IC is 3/2 mr squared. Now that we are here, let me also give you another example. I should have put more room in your notebook. So now I know for next year. But if you don't have enough room at the end of your notebook, there are some extra pages. Try to see if you can write T and U for this problem for me. K and M, and this is radius R. Just a simple example that we later will come back to it. But if you recall, we said two methods. We explained two methods. One, the Newton law, and the second one was the Lagrange equation, right? Lagrange equation, we take derivatives of T and U. So one step before using the Lagrange equation is to calculate T and to calculate U. So that's what we want to do for this problem. Try to think how it moves and what you can write the equations. By the way, do not forget, today is like tutorial 1 for half of you, and Monday is repeat of today's tutorial. You are free to attend any of these. And the tutorial is at the section 8 of your notebook, question that will be solved. If they have time, like the TAs, they have time, they will solve extra problems as well. Okay, so let's get to this problem. We have a disk, right? As I said, 3 things that you need to follow when you want to find the equation of motion for a system. The first thing is the kinematics. Try to figure out how this mechanism or this system is moving, right? That's the first step. Try to visualize it, build it in your mind, and see how it moves. So I have a disk, and then I have a spring, and this disk is being connected to the wall through this spring. So very simple. And let's assume that the question gives us this extra information that there is no slippage here. So no slipping. Okay, so that's all we know. So that's the kinematics. So we know how it moves. If I disturb this disk because it is at equilibrium, remember in vibration, we say free vibration, we disturb it and we see what will happen. If I disturb it, we know that the disk is going to come to the right, and then because of the spring, it's going to come back. So left, right, right, vibrates, which is the next things that we are going to be worried about. For now, we just want to find out T and V. The next step after kinematics, trying to find like a variable or coordinate for this system. So I can choose X, like this point O, I select X as that one. Or if you are dealing with a rotation system, maybe let's say theta would be a better choice. That's my coordinate or the variable that I have. Remember, we are in single degree of freedom. Either we are dealing with X, with Y, or with a rotation theta. So that's my variable or my coordinate theta. Right? So I have all this information. Now I should be able to write T and U. So T, and the system is at equilibrium at this point that the question show it to us, right? I disturb it by theta. So as a result, it moves and probably it will have some sort of a speed, omega. So what is T? We know it is more like a disk, the example that you just saw here. So I just need to write half of 3/2mr squared, that's IC. And omega in this case is, because my variable is theta, it is theta dot, right? And U is the amount that it's being deflected, which is the spring being deflected, half of K x squared, which X here simply can be R theta. Right? When it moves theta, the amount that the spring deflects is R theta. You may ask, what about mass or potential energy? So remember we said we have, let me write down. Mg. So remember we said potential energy, either a spring or mass, the gravitational potential energy. We had this rule that we look at the equilibrium position and see if the mass deflects the spring when we are at the equilibrium. Is there a static deflection in the spring? If there is, since they are going to cancel out each other, we don't include it into the equation. But in this example, there is no pre-deflection, pre-tension, or pre-compression in the spring because of the mass, right? So I should include it, right? So that's the rule. If there is no pre-tension or pre-compression in the spring because of the mass, it should be included here. However, I didn't write it. Why? Why I didn't write it? Technically, we should have like mg delta h, right? Exactly. Thank you. Because there is no delta h, right? The center of mass stay on a horizontal line, and there is no delta h. So this one is 0. So my equation for u is simply half of k r theta squared. So I have T and U, right? And you know how to use the Lagrange equation. Please spend some time later before the Monday class and try to take the derivative and find the equation of motion for this one. It will be super simple. Is there any question for this one? Okay. So let's like summarize so far. So far, we have been doing all review. Okay, so nothing really getting to the vibration. It was all review. We are now ready to move to actually to the vibration and solve some problem in vibration. Of course, we start with super simple problems. Please attend the tutorial either today or Monday. He's going to solve some simple problems so you become familiar and ready to start like the actual vibration. And also, now you have enough knowledge to start working on practice problems that I posted on Canvas. Okay, so you can work on the practice problem, and maybe for the quiz, maybe you should wait until Monday when we solve some other examples and you went through the TA, then you're ready also to work on the quiz as well. With that, have a good day, and if you have any question, I stay here. I have time. Hello. Let me wear my mask. So you see that they come after me.
My first question is, this one is simplified to just
Like if, you like this one. Yes. So we don't know what is B bar, but you can find B bar, B bar. Why?
Oh yeah. Sorry.
NG is delta H, but there is no delta H.
Yeah, but that's only the three components. Okay, perfect.
All right, no problem. Hello. Is it quick because we can wait? Yeah, stay outside if you have a question. I'm just gonna grab myself. I'll see you in a minute. No, here. Or they are going up there. Let's go up there.